This is our second video of Unit 8. With free energy diagrams under our belts, now we can learn even more about how enzymes work. This video will cover the 4 goals listed here. Pause the video if you want to check them out. We ended the last video by talking about how enzymes work to speed up reactions. Enzymes speed up reactions by reducing the activation energy of reactions. We can see an uncatalyzed reaction on the left with a very high activation energy. The reaction on the right is a catalyzed reaction with enzyme added, and you can see that the activation energy goes from one that's really unfavorable to an activation energy that's more favorable. This reaction right here is more likely to happen than this reaction over here. To know how enzymes really work, we've got to know a couple of things about them. First of all, enzymes are proteins. Now, there are exceptions to this, but for now, let's think about all enzymes as being proteins. It's oversimplification, but one that we can live with. Enzymes are catalysts, which just means that they speed up chemical reactions. Enzymes speed up chemical reactions by reducing activation energy. In the process of a chemical reaction, enzymes aren't used up. In other words, they're recyclable. You can see how an enzyme works right here. This is an enzyme at the beginning of a chemical reaction, and here's the enzyme at the end of the chemical reaction. The enzyme itself doesn't change, only the reactants change in going to the products. Another thing about enzymes is that enzymes are specific for specific reactions. An enzyme can't speed up any old chemical reaction, just certain ones, and we'll get into that in this video too. Another key point to tie back to our last video, is that you need to know that enzymes don't change the delta G of a reaction. Let's do a quick calculation of delta G for an uncatalyzed reaction and a catalyzed reaction. I'm just going to put some arbitrary numbers on there to illustrate the point. When you crank through the calculations, you see that delta G is -15 in both cases. Enzymes don't change delta G. In other words, the reactants and the products of an uncatalyzed reaction or a catalyzed reaction have the same energy properties. And when you figure out delta G, all you have to figure out is the energy level of the products minus the energy level of the reactants. So those two things aren't changing. The reactants and products are the same in catalyzed and uncatalyzed reactions. The only thing that's changed is the pathway of getting from reactants to products. An enzyme catalyzed reaction has a much easier pathway getting from reactants to products. One trap that's easy to fall into is the misconception that enzymes only help break down compounds, catabolic reactions, but there are enzymes that help in both anabolic and catabolic reactions too. In both of these examples on this diagram, the enzyme is this big old purple structure right here. On the top, the enzyme is helping break down one reactant into 2 products. Remember, a breakdown reaction is a catabolic reaction and an exergonic reaction like a hydrolysis reaction. On the bottom, the enzyme is putting together 2 different substrates to make one single product. This is an enzyme helping with an anabolic endergonic reaction like dehydration synthesis. There are some really important terms that we need to start off with here to make sure we have in place to understand enzymes. First, when talking about enzymes, instead of reactants, we say substrates. It's a little bit silly, but substrates are just reactants that are acted on by enzymes. But the good news is that we still call products products. That hasn't changed. I like to use the abbreviations S instead of substrate, P instead of product, and E instead of enzyme, just so I don't have to write as much. The important spot on an enzyme where the substrate binds is called the active site. So right here is the active site on the enzyme in this example. The active site is the most important part of an enzyme, and a part we'll go into more detail about in a bit. Now that we've laid a little bit of groundwork, let's go through how an enzyme works as a little more big picture. In other words, it's one complete reaction shown here, helped by an enzyme. In step 1, we see that the substrates are entering the active site of the enzyme. You can see in step 2 here that weak interactions hold the enzyme substrate complex in place. From our biochemistry unit, and remember that weak interactions include hydrogen bonds, ionic bonds, and hydrophobic, hydrophilic interactions, things like that. We're going to skip step 3 for right now, but we'll come back to it later. You can see in step 4 that the actual reaction has happened. The substrates have been converted into different chemical compounds as products. Step 5 down here shows the products being released from the active site of the enzyme, and this is where it's important to have those weak interactions. Weak interactions between the enzyme and substrate is what makes this release possible. If the enzyme substrate complex were stabilized by covalent bonds instead, those strong bonds, then it would be a lot harder to release the products once the chemical reaction was done. Finally, in step 6 over here, after the products are released, the enzyme is all reset and ready to do this process over again. So this is the basic catalytic cycle. But it's important to unpack some of the finer details between enzyme and substrate interactions. So how are enzymes specific for specific reactions? Well, the specificity comes from the complementarity between the enzyme and the substrate. We've seen this concept before when talking about the specificity between ligand and receptor binding. Just like in that case, it's the shape and chemical properties of enzymes and substrates that match up in order for the reaction to happen. In the example here, only substrate C has the correct shape to fit into the active site of the enzyme. Substrate A, B, and D won't fit. Hopefully, you could also imagine that if substrate C had a positive charge, then the active site of the enzyme must fit and have a negative charge. In our catalytic cycle example over here, you can see how the red and green substrates have a complementary shape to match the enzyme's active site, so both fit the enzyme just so. This specific fit is referred to as the lock and key model of enzyme function. Here are a few more examples of the lock and key model. You can see that the active sites of the enzyme fit the shape of the substrate. So that's the part that you can see. But what's hard to see, and you can't really see on here, is the complementarity and chemical properties too. So remember that. The chemical complementarity involves interactions like hydrogen bonds and other weak interactions so that the product can be released at the end of the chemical reaction. After studying enzymes and learning about them more, scientists found that the lock and key model didn't create a full picture of how enzymes work. So scientists refined this model into a model they called the Induced Fit Model. Now, the Induced Fit Model still has all the features that the lock and key model has. There's still complementarity of structure and chemical properties between the substrate and the active site of the enzyme. So the Induced Fit Model is like the lock and key model, but with a little bit more. That little bit more that's different about the Induced Fit Model is that the Induced Fit Model includes a slight shape change of the enzyme once the substrate is bound to the active site. So you can see here that the enzyme, which is a little more open on the left and closed on the right, the enzyme kind of hugs the substrate once the substrate fits in the active site pocket. You can see this before in the model that we were looking at. I just didn't bring attention to it. So the substrates here have a really nice complementarity with the active site of the enzyme, but once the substrates are bound, now the enzyme has changed shape. After the chemical reaction and the products are released, the enzyme changes back to its original shape. This is the Induced Fit Model. The lock and key model isn't wrong, and actually the lock and key model is in the Induced Fit Model. But the Induced Fit Model takes things a step further. Understanding the Induced Fit Model gives us really good insight into understanding how an enzyme helps speed up reactions. There are two mechanisms that you should feel really comfortable about. First, an enzyme changing shape helps the enzyme hold substrates in a certain way, and this is called substrate positioning. So, in anabolic reactions, bonds need to form between certain spots on the substrate, say like right here and right here between these two substrates. Normally, if those two substrates are just kind of floating around, the chances that these two spots would link up might be relatively low. But when both of these substrates fit in the active site of an enzyme in the perfect way, the enzyme can change shape a little bit to bring them together in a more favorable configuration so that these bonds can be formed and then the product is made. Another thing about how enzyme shape change in the induced fit model can explain how enzymes work is with this bond strain right here. So the enzyme changing shape can kind of flex the substrate in such a way to put some strain on the bonds. So now there's a lot of strain or stress on the chemical bonds of this substrate. Once the bond is strained, it becomes easier for the bond to break in catabolic reactions. These mechanisms of tying the induced fit model into how enzymes speed up chemical reactions are summarized in step 3 that we skipped over before. So, the enzyme acts as a template for substrate orientation. That's the positioning that we talked about. Stressing the substrates and stabilizing the transition state, that's the second thing that we talked about. Enzymes can also provide a favorable microenvironment in their active site, or enzymes can actually be a part of the catalytic reaction, where the substrates temporarily bind to the enzyme. So, hopefully the pieces are starting to fall into place in your understanding. There's one last thing that I want to talk about in this video, and that's how enzymes get their name. For right now, remember, we're going to say that all enzymes are proteins. Remember that proteins often have names that end in IN. Well, enzymes are proteins whose names don't end in IN, but usually end in ACE instead. Just like the kinases, enzymes that do phosphorylation that we saw before. In addition, most enzymes are usually named for the reaction that they catalyze. So let's check out these examples. This example here in the picture has the substrate of sucrose. The enzyme helps break sucrose into glucose and fructose. This enzyme is called sucrase, ends in ASE, and gets its name from the reaction that it carries out. Some other examples over here. Proteases are enzymes that help break down proteins. Lipases are enzymes that break down lipids. DNA polymerase is an enzyme that makes DNA polymers. We'll learn a lot about that later on. We already saw kinases, and kinase is a family of enzymes that do phosphorylation, and most kinases have another word in front. That's the substrate. Like MAP kinase is a kinase that phosphorylates MAP proteins. And of course, there's some funky exceptions to the rule, and one of these examples is pepsin. So pepsin is an enzyme that was discovered before this naming convention of ACE took place, and they knew that pepsin was a protein, but at the time that pepsin was named, it's a gastric enzyme. At the time that pepsin was named, all of these rules weren't in place yet, and then once the rules were put in place, everybody knew pepsin as pepsin, so they didn't want to change it. So let's recap. In this video, we learned that enzymes speed up reactions by reducing activation energy. But it's more than that. We learned how enzymes actually do this by looking at some models. The enzyme-substrate interactions are specific and dictated by chemical and physical complementarity between the substrate and the active site. The substrate and active site fit together with their shape and fit together with their complementary chemical properties. We talked about the induced fit model of enzyme function, and that says that substrates fit into enzymes like a key in a lock. So the locking key model is kind of boxed inside of that induced fit model, but that the substrate binding triggers a shape change of the enzyme. And that shape change helps position substrates to form bonds easier or to break bonds easier. All right, that's the basics of how enzymes work. And in our next video, we're going to look at some factors that change how enzymes work.